My dear students of CE806 bridge design, and today we will be giving the lesson number 6, and in this lesson 6 we will be dealing with shear reinforcement design. And there is a small table showing the shear values, as we have previously calculated the shear values for live load, wheel load and dead load. We have the list of the shear in the previous pages. From there I have just taken the short list of shear values for which we will be dealing in this section, in this part. And as you know that we have divided the bridge into 6 different parts. Number 1, 2, 3, 4, 5, 6. 6 is the extreme left support and 3 is the right support, and the mid span is the cantilever one and the simply supported one. Here we will be dealing with the shear in the end span, starting from bottom to top. It is 6 is our extreme end span. Then there is a 0.5 after 30 feet. Then 0.4 is after another 30 feet, and 0.3 is at a distance another 30 feet. And at the cantilever end, we will not design the cantilever end or the cantilever portion or the simply supported portion, because similar 60 feet or 50 feet bridge was taken care in the previous course 804. So leaving that part, keeping that away, there are 5 points, and actually it is 4 points. In shear design, this 3 left and 3 right doesn't mean anything, and that's why there is a single one shear we have taken as the value 345.1, and at 4 it is 188.4, and 5 it is 95, and at 6 it is 236.1. Now in the design we will be starting from the 0.6. At 0.6, as we have previously decided, the 0.6 cross section is 16 inch into 54 inch total. Total depth is 54 inch and width is 16 inch. And now we have to calculate the effective depth for designing the shear reinforcement and the steel main reinforcement. Here we will be anticipating that there will be about 3 layers of 1/3/8 inch dia main bar, and we will be using half inch dia stirrups, and there will be clear cover. As the beam is exposed to weather, the clear cover will be 2 inches, and there will be 3 spaces for 3 layer of bars, and 2 gaps between the bars. Using 1 inch as maximum size of coarse aggregate, we will find out the effective depth of this section at this section. 54 is the total depth, minus within the first bracket there are 2, 3, 4 elements. The number 1 is the 2 inch is the clear cover. 0.5 stands for stirrup diameter, and we anticipated that there will be 3 layers of rod. In actual field there may be a slight change, and that will not affect this design very much. And our estimate of 3 layer of 1/3/8 inch dia bar, and in the book this 1/3/8 inch dia bar, the actual inch dimension is given 1.41, not 1.375. You can look at the Nielsen's book in the appendix, and 1.41 is taken from that table where the bar diameter, areas and etc. are given. And there will be two gaps. Gaps will be for 3 layers of rod, there will be 2 gaps, and each gap we must keep the one gap as 1.25. How it is? We have taken the, as this is bridge and the structure has bigger dimensions, we have taken the maximum size of coarse aggregate as 1 inch, and we have to keep a gap of 1 inch into 1.25, that means 25% more than the maximum size of aggregate as a one layer, and there will be two layers of aggregate in between these 3 layers of reinforcement, and that's why we have taken this 2 into 1.25 inch. And after doing the arithmetic, we have found that this is 44.775, and we generally use half-inch division for a dimension of structure here. That's why 44.77 is taken as 44.5. Doesn't matter, because we have gone to this lower side, but very small lower size. And this is all for all practical purposes. This sort of things can be done. For girders, concrete strength is taken as 4 KSI, and transverse steel strength as 40 KSI. Here we have used for the girder in slab design. Maybe we have used 3 KSIs as the concrete strength and 60 KSI as the steel strength. Here we will be using, as this is girder, we will be using 4 KSI, and the transverse steel we can use the lower grade, because if we use higher grade then the spacing becomes too much, and in that case we don't want that big gaps, because there is a limitation of gaps by other conditions. That's why if we use 40 KSI, the stirrups will be closer, and that's why normally generally we use the strength of the stirrups as 40 KSI. Now, how much concrete will take care of this shear stress? First of all, for shear we have to use a phi value, 5 VC. Phi for shear is 0.75. In the next step, next portion you can see this. For 5 we have used 0.75. For shear, phi value is 75. For moment, phi value is 0.9. And there is a lambda factor, that means aggregate factor. Here we will be using concrete as bridge. In bridge we will not use brick aggregate. That's why lambda factor will be 1. We have put that lambda value as 1, and 2 is the coefficient of the equation. 2 for shear, how much shear the only concrete can take. This is the formula: phi 2 lambda root over f prime c. Bw is the width of the beam and d is the effective depth, and we have put these values: 2 for 2 and for lambda 1 and root over 4000, and 60 is the width of the beam previously decided, while we have taken this dimension of beam in preliminary lesson 16, and the 44.5 is the effective depth, and that gives us a value of 67.5 kb. This is equation. The equation written on the left hand side is referred to Nielsen's 5th edition. You can go Nielsen's 15th edition, you will see this equation. Next, spacing for stirrups taking half-inch dia bar with cross-sectional area of 0.2 inch square. And in Nielsen 5th edition, you will see equation 514.A. 514.A Nielsen. 514.A, the equation is S is spacing, and phi is, and again reduction factor, area of the transverse reinforcement. The transverse reinforcement area, the half-inch dia area has 0.2 inch square area. but we will everywhere we will be using 2 legs in the same section. That's why the AB is taken as 0.2 into 2, that is 0.4, and 40 is the Fy value we have taken for transverse reinforcement. We have taken this as 40 KSI, and 44.4 is the effective depth. And in the below the VU is the calculated shear 236.1, and the 5 VC, that much the concrete itself, concrete can take is 67.5 as we have previously calculated it, and that is 67.5. And then after deducting 67.5 from 236.1, we get a value like that, and the spacing is coming after calculation. We get it as 3.16, and we will be rounding it, and we will use 3 inch center to center. Question, we have given the equations of Nielsen 15th edition on the right hand side. This is the spacing, and now at this point, we have to check the how much is the maximum spacing requirement is the for the ACI from the ACI code. ACI code specifies that the maximum spacing should be d by 2, and for this section 44.5 divided by 2 is only 22.25. Therefore, our spacing 3 inches very far below than this value. There is another equation for finding of the maximum spacing of stirrup is AB FYT 0.75 root over F prime C into BWD, that is AB is 0.4 and FYT is 40,000 and 0.75 is 75 and root over F prime C is 4,000 and BW 16. Calculating this comes as 21 inches. And another requirement is S max is equal to AB FYT 50 BW. 0.4 is the AB and FYT is 40,000 and 50 is 50, BW is 16. That's why the spacing comes as 20 inch. Therefore, we have to use, after all the checking all these equations, we get a value of the minimum one is the 3 inch, and we have to use this here we have to use spacing of the stirrup as 3 inch center to center. Next page. Next page. Next page. At section 5, the result is 95 kips, and the section is same as section 6. So S max is equal to 75 is the 550, 75 is 5 factor, 0.4 is area of stirrup, and 40 is the allowable stress, and 45 is the depth D, and 95 is the value, and 67.5 is the concrete taking shear. Concrete taking shear, and that gives us a 19.6 as the spacing, and we will use this as 18 in center to center, and d by 2 and all other things remains they are same, and that's why the 18 in center to center is okay for this section. At section 5, the design shear value is 188.4 kips, and S4, that means if we keep the other value same, only the shear value is changing, and the value comes as 4.46, and we will be using 4 inches center to center. As section 2 is the part of the simply supported portion of the breeze, that is omitted because the same breeze was taught in CE804. As the total depth of 0.3, next the 0.3 has different depth, that's why we have kept it last. As the total depth at 0.3 we have chosen in the earlier calculation as 82 inch, effective depth is to be calculated, and the effective depth will be coming as 82 minus 12. There will be 3-4 layers of rod stirrups, there will be gaps for aggregate, etc., etc. We can we see in the previous case some value from the idea of that, where that value we can say that there will be a deduction of the effect for finding out the effective depth as 12. We have taken as 12. It will be little bit on the higher side, and if we are on the higher side, we are on the safe side. That's why we have taken D here, D as 70 inches, and here 5 VC with 70 inch, 16 by 17 inch, 5 VC, keeping all other things same. We have got this value as 106 kip. The 0.75 is the reduction factor. Then there is lambda factor and concrete strength, and allowable shear stress is 2 coefficient, and the 16 is the width of the beam, and 70 is the effective depth, as I have mentioned just before this line. That is 106 kip is the shear value. Using 5/8 inch, here we will be using little higher diameter, otherwise the spacing will be maybe too close there. And as the depth of the beam is big, that's why the higher diameter is more suitable. That's AV is 0.31 into 2 is 0.62. If we put all the values like previous calculations, then we get a value of 10.5 center to center, and we have to use 10 in center to center. 10 in center to center. So we have shown these values and at 0.6, 3, 4, and this is the end of this lecture, and tomorrow is our class. There is a class where you can discuss this one if you can go through it. If you do not understand anything, we can discuss this in the tomorrow's direct class. Thank you. ঠিক আছে? Yes. Similar.